Welcome. In this lecture, we are going to discuss about the Euclidean algorithm and see how we can use it to find GCD of positive integers. We begin by stating the Euclidean division lemma. Then we'll formally describe the Euclidean algorithm on how to find the GCD of numbers and then do some examples. Let's get started. So Euclid's division lemma states that if we have two positive integers, a and b, then there exist two integers q and r such that a can be written as bq plus r, and the number r should be between 0 and b. So this is the statement. So let a and b be any two positive integers and then we can, without loss of generality, let a be greater than b. Then they exist unique integers q and r such that this largest integer a can be written as bq plus r, where the number r lies between a and 0 and b. So from this statement, we know that one, the remainder is always less than the divisor. In this context, b is what we call the divisor. And two, if the remainder is 0, then a equals to bq. So b divides a. And number three, conversely, if b divides a, then a the same as bq. And so we just remember that by writing this, a is called the dividend, b is called the divisor, q is called the quotient, r is called the remainder. So that is how Euclid's division lemma states. So to appreciate this lemma, let's consider this appetizer. Given that there are 34 cakes, and each box can hold 5 cakes each, or 5 cakes only. how many boxes we need to pack and how many cakes are unpacked. This is a good appetizer to appreciate the Euclidean division lemma. So from this statement, we know that six boxes are required to pack 30 cakes with 4 cakes left over. This distribution of cakes can be understood as follows. So we can do this. We draw a small table So we have 34 is equals to 5 times 6 plus 4. Where in this table, 34 is the total number of cakes available. 5 is the number of cakes in each box. Then 6 is the number of boxes packed. Then 4 is the number of cakes left over. So note that this number 34 in this context is called the dividend. So where in general is what we are calling A. This 5 is what we call the divisor. B. Then 6 is what we call the quotient, called Q. And 4 is what we call the remainder, what you are calling as R. So then now, this allows us to give a generalization of the Euclidean lemma, which is going to help us to find remainders when you're doing some division of integers. So generalized form of Euclid's division lemma. So if A and B are, and the condition is that this B is non-zero number, any two integers, not necessarily positive, then they exist unique integers Q and R such that A is always the same as BQ plus R, where 0 is less than or equals to R is less than the absolute value of B. So that's what we call the generalized form of the Euclid's lemma, or division lemma. It applies for any arbitrary two integers, A and B, where B must be non-zero. So A, in this context, is still the dividend. B is the divisor. Q is a quotient. And R is the remainder. So we can do some examples to illustrate how generalized Euclid's division lemma states. So in form of a question, find the quotient and remainder when A is divided by B in the following cases. So the first problem, A, or Roman 1, A is minus 12, B is given by 5. Roman 2, A is 17, B is minus 3. And Roman 3, A is minus 19, B is minus 4. So this is what we do. So for Roman 1, we know that by Euclid's division lemma, A is the same as BQ plus R, where 0 is less than or equals to R, less than or equal to absolute value of B. So we have minus 12. So we need to get the quotient when we divide minus 12 by 5. So we clearly see that when we multiply minus 3 by 5, we get a number which is minus 15, which is the closest multiple of 5 less than minus 12. And then the remainder will be 3. And this can be seen that R is a number between 0 and absolute value of B, which is 5. So 3 is less than 5. So therefore, the quotient is minus 3, and the remainder is positive 3. Then Roman 2, similarly by Euclid's theorem, Euclid's division lemma, we have A is equals to BQ plus R, where 0 is less than or equals to R less than absolute value of B. And in this case, A is given by 17. So we need to get the closest multiple of minus 3 less than or equals to 17. And we realize that that multiple will be 15, which is given by minus 3 times minus 5. And then the remainder will be 2. And you can clearly see that 0 is less than R, less than absolute value of minus 3. So therefore, here Q will be minus 5, and R is positive 2. So the remainder is positive 2. The quotient is minus 5. Then part 3, also by the division algorithm, the Euclidean division lemma, we have that A equals to BQ plus R. R must be between 0 and absolute value of B. So in this case, A is given by minus 19. We need to get the closest multiple, our B in this case is minus 4, to our closest multiple less than or equals to minus 19 of minus 4. And that will be minus 20, which is given by minus 4 multiplied by 5. And the remainder in this case will be 1. So clearly, Q is 5 and R is 1. So that is how we can use the generalized form of Euclid's division lemma to find quotients and remainders when we are dividing two arbitrary integers. So at this point now, we are able to, or we can now state the Euclidean division algorithm that is going to help us to find GCD of integers. So Euclid's division algorithm, or some call it the Euclidean the division algorithm or Euclidean algorithm. So this algorithm makes it easier for one to find the highest common factor or the greatest common divisor of any two arbitrary positive integers. But as we shall see later on, we can as well apply it repeatedly to find the GCD of three positive integers. So this algorithm provides an easier way to compute the highest common factor. We call it HCF, or we call it greatest common divisor, abbreviated by GCD, of two given positive integers. So let's now give the theorem on how this really works. So theorem, if A and B are positive integers, such that A is the same as BQ plus R, then every common divisor of A and B is a common divisor of B and R, and vice versa. And if A and B are positive integers such that A can be written as BQ plus R, then every common divisor of A and B is a common divisor of B and R, and vice versa. So we now give step-by-step procedure on how to use Euclidean division algorithm to find GCD of two positive integers A and B. So Euclid's division algorithm. For finding GCD of two numbers A and B. So to find the highest common factor or the greatest common divisor of two positive integers A and B, where A is greater than B, we follow the following steps. So the first step, use Euclid's division lemma A equals to BQ plus R, where 0 is less than or equals to R less than B, where Q is a quotient, R is a remainder, so if R equals to 0, then the GCD of A and B is B. So that's the first step. And then step 2, assuming that's not the case, if you don't find the remainder to be 0, or remainder is a non-zero number, then step 2 says, otherwise, apply the Euclid's lemma applying the Euclid's division lemma, divide B by R to get B equals to RQ1 plus R1, where 0 is less than or equals to R1 is less than R. Step 3, if R1 is 0, then R is a GCD of A and B. So we find that the second remainder is 0, then the previous remainder R is the GCD of A and B. What if R1 is not 0? So otherwise, using Euclid's division lemma, repeat the process until we get the remainder 0. In that case, the corresponding divisor is the GCD of A and B. In simple terms, I mean, the GCD of A and B will be the previous non-zero remainder after you have exhausted all the Euclidean division lemma process to the point where your R is 0. So the previous R value is what will be the GCD of A and B. So note one, the above algorithm or procedure will always produce remainder 0 at some stage. You must always do the whole process up to the point where R will be 0. It's always guaranteed. Hence, the algorithm should terminate. That's point number one. But the repeated application of the Euclidean algorithm will always go up to the point where the remainder is 0. Number two, the Euclid's division lemma or algorithm is a repeated application of division lemma until we get 0 remainder. And then number three, GCD of two positive numbers. In this case, we are dealing with integers, is denoted by or simply so that's how we denote the GCD of two positive integers A and B. So at this point, we are now mature to do some examples on how we can apply the division algorithm or the Euclidean algorithm to find GCD of positive integers. So appetizers. So find the GCD of the following numbers using the division algorithm. So the first pair is 273 and 119. So remember that we need to write this as A plus BQ plus R, then repeatedly apply this division lemma up to the point R will be 0. And so the GCD will be the previous non-zero value of R. The solution, without loss of generality, let A to be 273 and B be 119. So 273 will be given by 119 times 2 plus 35. You should check that now 119 by 2 is the closest multiple 119 to 273. Closest multiple is less than or equals to 273. So we can call this one equation 1. And then now in the next process, because the remainder is 0, your A becomes 119, the previous B value, and your B becomes your previous R value, which is 35. So you realize that the closest multiple less than or equals to 119 of 35 is 35 by 3. And then the remainder here will be 14. So this step 2. If the remainder is non-zero, so we move on. So the new A becomes 35. Our new B becomes 14. And the closest multiple 14 less than or equal to 35 is 28, which is given by 14 by 2. And the remainder will be 7. This is step 3. And we see that the remainder is still non-zero. Move on. So that in the next step, A will be 14, B will be 7. So you have 14 equals to 7 by 2. And this one we get that the remainder will be 0. So the previous non-zero remainder is usually the GCD of the two numbers A and B. So therefore, GCD of 273 and 119 is nothing but 7. So problem 2, we have the numbers 414 and 662. So then now, so here, without loss of generality, let A to be 662 and B be 414. So by division algorithm, we have A equals to BQ plus R. So that 662 equals to the closest multiple of 414 less than or equal to 662 is just 414. So we'll have 414 times 1 plus remainder is 248. Then the new A becomes 414, new B becomes 248, and 248 is the closest multiple of 414 less than or equals to 414 itself. In this case, the remainder will be 166. So that's the second step. The third step, your new value of A becomes 248. Our B value becomes 166. Still, the closest multiple of 166 to 248 is 166. The remainder will be 82. This is number 3. Then our new A becomes 166. B becomes 82. And then the remainder in this case becomes 2. So the next A value will be 82. Our B value becomes 2. Then the quotient will be 41. So then plus 0. So at step 5 is when we are getting the remainder to be 0. So this previous non-zero remainder will be the GCD of (414) and 662. So that will be the GCD of those two given numbers. Then example 3 states that the GCD of 210 and 55 is expressible in the form 55x minus 325. Find the value of x. What this problem requires us to do is to use division algorithm to find the GCD of 210 and 55. Then after we have the GCD, we equate to 55x minus 325 and solve for x. So we use the Euclidean division algorithm to evaluate the GCD of 210 and 55. So without loss of generality, let A to be 210 and B be 55. So then you remember that we have now to go through the process of A equals to BQ plus R, such that R is always between 0 and B. So 210 is the same as 55 times 3 plus 45. Then our new A becomes 55, our new B becomes 45, and 55 is the same as 45 times 1 plus 10. So if the remainder is not 0, then we go on. Our new A becomes 45. Our B is 10. Quotient will be 4, and the remainder will be 5. Next step, our new A becomes 10. Our new B becomes 5. Quotient will be 2. Remainder will be 0. So this previous non-zero remainder is a GCD of 210 and 55. So this implies that GCD of 210 and 55 is equals to 5. And because we are told that the GCD is expressible in the form 55x minus 325, so this means that this 5 is the same as the given, which is 55x minus 325. So which means 55x is equals to 5 plus 325. Then 55x would be the same as 330. When you divide by 55, divide by 55, you get x is equals to 6. So the value of x is 6. Example 4. Find the greatest common divisor that will divide 445 and 572, leaving remainders of 4 and 5 respectively. These sound more or less the same as high school problem. So the required number is a GCD of 445 minus 4, which is 441, and 572 minus 5, which is 567. So by division algorithm, we let our A to be 567, and this is the same as 441 times 1 plus 126. Our new A becomes 441, B becomes 126 times 3, plus the remainder will be 63. Then our new A is 126, new B is 63 times 2, then plus 0. So which means that the GCD of these two numbers is this previous non-zero remainder. So therefore, GCD of 441 and 567 equals to 63. And so the required number is 63. At the start, we said that we can also apply division algorithm to find the GCD of 3 positive integers A, B, and C. So let's quickly show how we can do that. Highest common factor, or GCD, of 3 numbers by Euclidean division algorithm. So we can apply the Euclidean division algorithm twice to find the GCD of 3 positive integers using the following procedure. So let A, B, and C be any 3 positive integers. So step 1, find GCD of A and B and call it D. Then step 2, find the GCD of D and C, call it E. So the GCD of A, B, and C will be the same as the GCD of D and C, which is E. So for example, let A be 396, B let's just give them in general form. Find the GCD of 396, 504, and 636 using Euclidean Division Algorithm. So solution, let A be 504, B be 396, and C be 636. So A equals to BQ plus R, i.e. 504 equals to 396 times 1 plus the remainder in this case is 108. Our next step, A will be 396. Our B will be 108. Quotient in this case will be 3 plus the remainder is 72. New A becomes 108, B becomes 72. Then quotient is 1, remainder will be 36. Next step, A will be 72, B 36, quotient will be 2, and the remainder will be 0. So it tells us that this number 36 must be the GCD of A and B. So therefore, GCD of 396 and 504 is 36. So this is like what we used to call D. So next, we find GCD of C and D, i.e. GCD of 36, and the next number is 636. So we write 636 equals to 36 times 17 plus 24. Our new A becomes 36, our new B becomes 24. Quotient will be 1. and remainder will be 12. Our new A becomes 24, B is 12, quotient is 2, and the remainder will be 0. So this is means that the GCD of 636 and 36 is 12. So therefore, GCD of the three given numbers, 396, 504, and 636 will be 12. So before we wrap up, there's what we call Bedou's theorem, which simply states that the GCD of any two positive integers can be expressed as a linear combination of the two integers. So Bedou's theorem expresses the GCD of two integers as a linear combination of the two integers. So if A and B are positive integers, then they exist integers S and T such that the GCD of A and B is nothing but SA plus TB. In simple terms, GCD of two positive integers A and B can be written as a linear combination of the two integers A and B. So there's a definition with respect to this theorem. So definition, if A and B are positive integers, then S and T such that GCD of AB is equals to SA plus TB are called Bedou's coefficients of A and B are called Bedou's coefficients of A and B. Also, the equation GCD of A and B equals to SA plus TB is called Bedou's identity. So Bedou was a French mathematician of the 18th century. So let's quickly describe how we can find the Bedou coefficients when we have two positive integers. So example, express GCD of 252 and 198 as a linear combination of 252 and 198. So this is how we do the problem. You work through the division algorithm to find the GCD, and then reverse the process to enable you get S and T. So solution, step 1, use the Euclidean division algorithm to find GCD of the two numbers 252 and 198. So we have 252 equals to 198 times 1 plus 54. Then our new A will be 198 is the same as 54 times 3 plus remainder is 36. The new A becomes 54, which will be 36 times 1 plus 18. Can call this equation 1, call this equation 2, call this equation 3. The next step, our new A will be 36, our B will be 18. I multiply by 2, and I get the remainder to be 0. So whenever we get the remainder to be 0, then we stop at that point. And so that is the GCD. So this implies that GCD of 252, 198 is given by 18. So that's the first step. So step 2, reverse the steps in one above. So I mean, from the line where we have 18, you make 18 the subject. So you write 18 equals to 54 minus 36 times 1. Call it, say, equation 1. Call it maybe, say, 5. Then from line 2, we have, so you see from line 2, we know the value of 36. So 36 is the same as 198 minus 54 times 3. So use this value in 1, in 5 to get 18 equals to 54 minus, instead of 36, I write 198 minus 54 times 3, then times 1. We can simplify this as 18 equals to, now this is 154, and then this we are minus 1 times 3 is 3, so minus 3 54s, and then 154 will give us minus. Remember there's a minus here, this minus times this one. So when I open the brackets, this sign will be plus. So 354s plus 154, I'll get 4 of them. So 54 times 4 minus 1 times 198. So call this one 6. Then from line 1, we know what is 54. So from line 1, 54 is equals to 252 minus 1 times 198, or 198 times 1. So therefore, question 6 becomes 18 equals to, instead of 54, I write 252 minus 1 times 198. I multiply by 4 minus 1 times 198. So I'll have 4 times 252 and then 4 times minus 1 is minus 4, minus 198, I'll get minus 5 times 198, i.e. GCD of 252 and 198 is the same as 252 times 4 plus 198 times minus 5. And you should check that when you simplify this, you get the number 18, which is the GCD of the two numbers, 252 and 198. In the next session, we'll be discussing about modular arithmetic, how we can include the aspect of division algorithm to solving modular arithmetic problems. Thank you.